Welcome everyone. Today I have a pleasure to introduce Cecile from Grenoble, LPMMC. So Cecile did her PhD in ENS Paris in 2015 under Nicolas Renaud. And there she was working a lot on fractional quantum Hall effect and topology, related topology to that. In 2017, in 15 already, she moved to Max Planck, Dresden, where actually I met Cecile and we kind of overlapped for 2 years almost during both of our postdoc. Then in 2017, Cecile moved to MIT for another postdoc with the same thing. And there she stayed for 2 more years. And only last year in 2019, Cecile again came back to France and in Grenoble, where she got a permanent position. So thank you, Cecile, for joining, taking our invitation and giving this talk. So she will be talking today about ferromagnetism and quantum anomalous Hall effect in twisted bilayer graphene. Thank you, Cecile. You can start.
Okay, well, hello everybody, and thanks Shomo for the kind introduction and for inviting me to speak. So indeed I'll be talking about twisted bilayer graphene and some of the many strongly correlated phenomena that can be observed in this new and exciting material. And more specifically, I'll be presenting some results of unbiased numerical calculations that I did in this system along with some of my MIT collaborators. So as I'm sure you know at this point, twisted bilayer graphene is the system that you can obtain by taking 2 single layers of graphene, stacking them on top of one another and twisting them with a small angle that you can control actually quite well. And what's extremely interesting with this system is that it's an extremely versatile platform for strongly correlated phenomena. And the reason for that is that by twisting the angle, you can actually act on the band structure of this material and obtain a very large density of state as specific energies. So that means that you can obtain a very large ratio of interaction over bandwidth, where bandwidth is this W here, which is the condition to obtain strongly correlated physics. And there's another thing that makes twisted bilayer graphene a very nice platform is the possibility to gate it, which is same as graphene or the 2D materials. It's possible to add a gate, and just by changing the potential of this gate to tune the chemical potential in the sample, which if you had a more regular quantum material, you'd have to do some chemical doping to change that property. So thanks to this property, to this nice versatility and these properties, twisted bilayer graphene has emerged as a really nice platform for strongly correlated phenomena, and in particular, experimentally, very striking phenomena have been observed. One of them is some correlated insulators at various commensurate fillings, as well as superconductivity, maybe most strikingly, but also ferromagnetism and a quantized anomalous Hall effect. And the purpose of this talk will be to talk about these 2 last phenomena and explain how they rise in twisted bilayer graphene and also in some other moire materials. So here is the outline of my talk. I will start by some general and broad reminders about the basic physics that I will be talking about, namely quantum anomalous Hall effect and its relationship with ferromagnetism. Then I will move on to some explanations about the band structure of twisted bilayer graphene at magic angle, the angle that allows this strongly correlated phenomena, before moving on to the role of interactions, really the heart of the work that we did, and showing you some results, mostly of exact diagonalization, to show how the ferromagnetism emerges thanks to nearly flat bands. And finally, if time permits, I will go beyond integer commensurate filling and talk a little bit about the possibility of observing fractional anomalous Hall effects in the same systems. So let's start with some reminders about quantum anomalous Hall effect and also its relationship with ferromagnetism. So as you all know, the Hall effect is the phenomenon that arises when you have a material which is in a magnetic field and there's a current going through this material. And because of the magnetic field, you can observe a voltage that is perpendicular to this current. And within a classical treatment, the corresponding resistance is just proportional to the magnetic field. Of course, if you go to the quantum regime in low dimension, so if you go to a two-dimensional system, such as gallium arsenide quantum world or graphene, and if the temperature is sufficiently low, the magnetic field is sufficiently strong, then this relationship, this proportionality is no longer true, but you will observe these plateaus of the whole resistivity. Namely, the whole conductivity will be quantized to integers times the quantum of conductance E squared over h, where this quantity does not depend on any details of the material or on the disorder realization, because this is a quantity which is very robust because it's a topological invariant. So that's, broadly speaking, the Hall effect, and more specifically the integer quantum Hall effect. Now, the Hall effect can, in principle, also emerge in the absence of a magnetic field. And actually, there's some analogies between the two phenomena, the Hall effect and the anomalous Hall effect, which doesn't require a magnetic field. So if you have a magnetic field, you know that if you have an electron that goes around a loop, it will pick up a phase which is equal to the integral of the magnetic potential around this loop. This is the Aharonov-Bohm effect. Now, in a solid system, if you have an electron that goes around the loop, not necessarily in real space, but in the Brillouin zone, in K space, then it will also pick up a phase which is determined by the band structural properties. Actually, this phase is called the Berry phase, and it can be determined purely based on the eigenstates of this lattice system. So it's purely given in terms of the Bloch wave functions. So there's this very strong analogy between the Berry connection, which is defined here in terms of the Bloch wave functions, and the magnetic vector potential, and also between the magnetic field and the Berry curvature, which can be thought of as a magnetic field in momentum space. Because of this, it's possible for a material to have a whole conductance, sigma h, which is non-zero, even though the magnetic field itself is zero. And if you have an insulator, this whole conductance actually has to be quantized. And it will be quantized to an integer called C, called the Chern number, times the quantum of conductance E squared over h. And this is what we call the quantized anomalous Hall effect. Anomalous because it doesn't require a magnetic field. What it requires, though, is to break time reversal symmetry, because sigma h is odd under time reversal symmetry. Not breaking the symmetry means that sigma h has to be zero. So here I'm giving an overview of the similarities and also the differences between quantum Hall effect and quantum anomalous Hall effect. So on the left, I have the spectrum of an electron in 2 dimensions under a magnetic field. So it's made of this macroscopically degenerate levels called Landau levels. And on the right, I have a band structure, which is very generic, corresponding to some two-dimensional lattice. But instead of having many, here I've just taken one band, and this band has a time reversal conjugate, which is at the same energy, but has the opposite Chern number. Meaning that if I want to obtain a non-zero Hall conductance in this system, I need to somehow polarize the system into one of the bands. So this is where ferromagnetism comes into play, because you need this polarization to be able to see a non-zero sigma H. It also means that the behavior of these two types of system under a magnetic field will be quite different. In the regular quantum Hall effect, as you change the magnetic field, you go through different plateaus of the whole conductivity. In the quantum anomalous Hall effect, really what you have is a magnet. So what you expect is a hysteresis loop, where for strong magnetic field of a given sign, you will polarize the system into one of the bands and thus see the quantized Hall conductance of C E squared over H. But as you decrease the magnetic field, you will go through a regime where the magnetic field is zero, and yet the system is still polarized, and therefore you still have sigma H, which is non-zero and quantized, such as what you see here. So more physically, there are various ways you could realize this sort of phenomenon. Actually, the first time that it was observed, the first time it was realized, was in magnetically doped topological insulator thin fields, meaning that this time reversal breaking I was talking about was really created by adding ferromagnetic perturbations. So time reversal symmetry was broken explicitly because of this magnetic doping. More recently, in 2019, the same type of quantum anomalous Hall effect was observed in twisted bilayer graphene aligned with a substrate of hexagonal Boron Nitride. But in this case, there was no doping, and the time reversal breaking is actually spontaneous. So this is what I will focus on during this talk, and this is what I will now go into details about. So let's talk a little bit about the band structure of twisted bilayer graphene. So to start, we just take one layer of graphene. As you know, graphene is this hexagonal array of atoms, of carbon atoms, and you have two sublattices, sublattice A, sublattice B. And if you go to momentum space and you look at the spectrum of this structure, you will obtain two bands which touch at the corners of the Brillouin zone, the K and K prime points. And wherever they touch, there is a linear dispersion relation. There's a Dirac cone around the Fermi energy. So you have two, we call those valleys at K and K prime point. They are the two inequivalent points, two inequivalent corners of the Brillouin zone, and you also have two spins. Now I'm taking two layers of this, and I'm stacking them on top of one another with a small rotation angle between them. So what I obtain is this moire superlattice. So there's a superlattice because the two Bravais vectors of graphene don't match anymore, and you have this very large unit cell of thousands of carbon atoms. And if I think about this in momentum space, I can imagine this starting from the case where the two layers are aligned and where the Dirac cones of the two layers coincide. And if I include a small angle, and I'm starting to separate them slightly. And now I will have to define a new Brilliant zone. And because I have increased my lattice constant by a lot, it means that the Brilliant zone will be reduced a lot. Sometimes it's called a mini Brilliant zone. Okay, so in case space now I have this mini Brilliant zone, meaning that all this dispersion of graphene has now been folded onto itself to form several bands at various energies, with the Dirac cone always around 0, and then a symmetric spectrum on other side. And at all these points of foldings, and also wherever the dispersions of the two layers meet, I have some crossing, but these crossings are not protected. So as soon as I allow some interlayer tunneling, which of course exists in bilayer graphene, there will be level repulsion forming several separate bands. And we will focus on the valence and conduction bands, which are still connected by Dirac points. Now, what makes the system very interesting, as I've said in the introduction, is the possibility to obtain very narrow bands, to have a very small bandwidth. And this occurs at some very specific angles called magic angle. And the largest of those magic angles is around 1.1 degree. So as you reduce the angle, you will also change the nature. You will bring the Dirac points closer, but you will also change the superlattice potential coupling the two layers. And this is the interplay of these things is what will result in this magic angle condition where the Fermi velocity vanishes and where the band is almost flat and the bandwidth is almost 0. So here I am actually interested in adding another step to this band structure. Well, cannot really call it a derivation.
Cecile,
Yes. Yes.
we have a question. Would you like to take it now?
Sure. Yeah, I can
Yeah,
take it now.
Sumiran, go ahead.
Sorry, I just got confused on the diagram before in the previous slide.
In this slide?
Yeah, in the third panel, somehow VF goes to 0 in the figure, right?
Yes.
How did that happen? Is that what you're going to explain next?
No, so I'm not going to get into details of this.
Okay.
I think this is a calculation that you can do but it's possible. So the idea of the Bistruster-McDonald model, which is the one that I'm using and that is very often used in this field, is just to take a continuum model of graphene around the Dirac cone, to take two layers of this with an angle, and then add the superlattice potential corresponding to coupling these two layers together. Yeah, the fact that there is a magic angle condition comes out of that. I don't really have an intuitive way of explaining it.
Okay, thank you.
All right, so I want to add an extra ingredient to this, which is to add a mass to gap out the Dirac cones. Indeed, in graphene, the Dirac cones are protected by a symmetry, which is the product of C2, the symmetry that, which is a rotation by 180 degrees, and T, time reversal symmetry. So if you break C to T, you can actually, you can gap out the Dirac cones. And it's exactly the same in twisted bilayer graphene. So this is actually realized when you align this system of twisted bilayer graphene with its substrate of hexagonal boron nitride. So, so this is this is the substrate that is very often used for these systems, and it is hexagonal. But unlike graphene, the two sublattices are not made with the same atoms, and they're not symmetric. It doesn't have sublattice symmetry. So effectively, if you align one of the layers of graphene with the substrate, the result will be to break sublattice symmetry for graphene, which breaks C2. So it basically introduces a mass that gaps out the Dirac cones. So now conduction and valence bands are separated by a single particle gap. And now if I take a broader view at the Brilliant zone, I can focus on one valley here, the red dots, and wonder if I just what is the Chern number of these bands? Since now they are gaps, they have a well-defined Chern number. And in fact, this Chern number will be non-trivial. It will be 1 because you've taken together the Dirac cones with the same chirality. So it will be, say I'm taking valley K minus, the valence band will have a Chern number -1 for both spins. And the conduction band will have the opposite Chern number, Chern 1, again for both spins. And in this system, time reversal maps one valley onto the other. So if I apply time reversal, I will get the other valley, but with opposite Chern number. So the valley plus has a valence band with Chern number 1 for both spins, and the conduction band with Chern number -1, again for both spins. So this is where we now connect with the what I showed a few slides ago, that if you're able to somehow polarize the system into one of the valleys, you can observe an anomalous Hall effect, because there will be, if you polarize into one of the valleys, then there will be an imbalance between Chern 1 and Chern -1, with the net effect of having a non-zero Hall conductance. So now what I want to talk about is how that actually happens, and this will be due to the strong interactions in the system. So now we move on to the role of interactions, and namely the ferromagnetism of nearly flat bands. So in atomic physics, there's a rule called Hund's rule that you're probably familiar with, which tells you that if you have degenerate atomic orbitals, it is energetically more favorable to fill up these orbitals with as many spins with the same orientation as possible. And this is due to having an exchange term that makes this state lower in energy than this term. And in fact, this same rule applies in solid states. And here the concept of degenerate atomic orbitals is replaced by the concept of a flat band. So if you have a perfectly flat band, it's energetically more favorable to, and if you are half filling, it's better to put all the spins in the same direction rather than having some imbalance of spins. So this is due to, there are many ways to think about this. Probably the most intuitive ways is if you have only two sides and you consider the electrons on this side, and if you realize that having a low electronic density in the middle will decrease the repulsive interaction between those two electrons, you will see that it's more favorable to have a wave function that is spatially antisymmetric, such that the spins in turn will have to be symmetric. So they'll have to be ferromagnetic. But this can be generalized, and this can be seen in a more formal way. For example, if you have a trivial band, then you can always build localized 1E wave functions for these bands and define an effective exchange interaction between different sites. And because of the repulsive character of the interaction, then there will be a ferromagnetic intersites exchange, which depends on the overlap between these 1E wave functions, so that even if the bandwidth goes to 0, as long as the overlap between the wave functions stays finite, then this term will not vanish. Then more generally, and especially if you have a Chern number and you cannot define sites like this, cannot define 1U wave functions that are localized, you can actually treat this problem within mean field, do Hartree-Fock, and you'll find that the ground state is indeed ferromagnetic. And in the context of moire graphene, this was actually calculated before. So all of this is, of course, was studied a lot in the context of the quantum Hall effect. This is typically called the quantum Hall ferromagnetism. And we understand very well why, because the Landau levels of the quantum Hall effect are the best example we have of a flat band. So this is why this concept of flat band ferromagnetism applies especially to quantum Hall systems. So in our work, we wanted to go beyond mean fields and bring both some analytical and also numerical arguments why it makes sense that this ferromagnetism is observed in twisted bilayer graphene aligned with hexagonal boron nitride. So let's start with some analytical arguments that can give some intuition to start with. So here are the hypotheses of the problem. So I have again my valence and conduction band here, and I have defined this as delta as the gap between them, and W as the bandwidth, which is supposed to be very small. So we are working in the limit where the flat band limit, meaning that the bandwidth is much smaller than the interaction strength. And we also want to avoid any band mixing. So we want the interaction strength to be much smaller than the band gap. So in practice, this is not necessarily always the case in twisted bilayer graphene. Actually, these can be sort of the same order of magnitude, but this is a good starting point to understand the physics. So the Hamiltonian we're looking at in this limit is a projected Hamiltonian. Indeed, in this limit, we can forget about remote bands, project the interaction onto the active band. Let's say it's the conduction band, and the bandwidth is so small that we can neglect any kinetic energy term. So we only have this interaction term, which I have written here in K space as V of Q times rho Q rho minus Q. So rho Q is a projected density operator. V of Q is actually it could be any repulsive interaction, but of course, realistically, it's a screened Coulomb interaction. And for the projected density operator, these involve a density which is normalized by a form factor, which depends on the single particle wave function, so the Bloch wave functions, as written here. And the total density operator takes into account all spins and all valleys. So it takes into account the fact that each of these bands is fourfold degenerate because of spin and valley. So now the argument goes like this. So first of all, we can notice that the Hamiltonian is positive semi-definite. Why is that? Because so rho minus Q is actually rho Q dagger. So if you have a product of A and A dagger that is positive, that will be positive semi-definite. And V of Q is positive because we have a repulsive interaction. So each term in the sum is positive semi-definite, and as a result, H also is. So if you can find a state that satisfies H psi equals to 0, then you'll know that this state has to be a ground state of the Hamiltonian. And it turns out that we can. So in this situation, we want to consider integer filling. What that means in this context is, for example, filling 0 would be having the Fermi level in the gap here. A filling 4 would be to have it above the conduction band. Filling 1 would be if, for example, if it's basically a quarter of this band. So if I fully polarize, if I fully spin and valley polarize, then this is a state that has a filling 1. And it turns out that this state, this fully polarized state, satisfies rho q psi equals to 0. So for any q, actually there's a small caveat for this because you need to be in the first Brilliant zone, but we'll just neglect the terms that are outside of the first Brilliant zone. So because of this, this spin and valley polarized wave function satisfies H psi equals to 0. Therefore, it is a ground state of this Hamiltonian. It doesn't prove that it's unique, but it proves that it's a ground state. So for these arguments, I was really relying on the fact that W, the bandwidth, was much smaller than the interaction strength. And if I want to go beyond that, and if I want to study the effect of a non-zero bandwidth, and if I want to be quantitative, then I really need to do numerics, which is what we did. So, so here is the model that we're using. This is the one I've presented earlier in the talk, the band structure, the continuum model in K-space. It's the distributed hexagonal model. It has a number of symmetries, which is that the total valley number is conserved. It's a good quantum number. And for each valley number, the SU2 spin symmetry is also conserved. And it's typically considered a good, relatively well realized in the system of bilayer graphene or moire graphene in general. Then the Hamiltonian we're using is again this this Coulomb interaction, actually screen Coulomb interaction, V of Q, rho minus Q, where the rhos are projected onto the active band, the valence band. And then we have added a dispersion term. So this is just a kinetic energy with bandwidth W. So here,
Cecil, we have another question.
okay.
Yes, Sumiran.
So this conservation of the valley charge, is it meaning that individual valley charges are conserved individually?
Yeah, it means that yeah, you have a valley number, which is how many electrons you have in valley plus minus
So that
how many electrons you have in the other valley, and that number is conserved.
the number of electrons in one valley is conserved, right?
Yes.
And that is because you have a discrete Coulomb interaction. Is that roughly the reason?
Well, here the two bands are really, if you compare with graphene, the two bands are really now separate in terms of their, in terms of that dispersion relation.
I mean,
So
the thinking is, say in graphene, if I have scattering between the two valleys, then I need not have this conservation, right? Which can be done.
yeah, that's correct. Yeah, we just assumed. I mean, we just figured this term is very small.
Okay, okay, and okay.
Yeah. Okay, so I was commenting on this second term of the Hamiltonian, which corresponds to adding a finite bandwidth to my initially fully flat band. And as you can see here, I've chosen a somewhat artificial dispersion for it, instead of, for example, something that would be derived from the Bristol-Macdonald model or something that is more realistic. The reason for this is that we don't necessarily know with a lot of precision what is this kinetic term or what is this bandwidth. And actually trying to figure it out would require some pretty, some calculations that take into account, for example, the remote bands. If they have some influence because of interactions, they do renormalize the bandwidth. Here, this is not really the philosophy of our work to try and derive a very realistic dispersion, but rather we want to know generically how robust this phenomenon is once you add some dispersion. And we just assume that the exact form of the dispersion is not going to have a very important role, but rather the strength of the bandwidth is what is going to really determine whether the flat band ferromagnetism will survive or not. So here are some results obtained with exact diagonalization. So what we are representing here is the maximal bandwidth that you can have in the system before you kill the ferromagnetism, before the system is no longer fully valley and spin polarized. Of course, it's clear that this has to happen at some point, because if W is the only term in the Hamiltonian, then you should obtain a family liquid, which has no polarization. So here we see that depending on which exact model we use, we get from 5 to 20% of interaction strength before we kill the ferromagnetism. So here the different colors correspond to different models, different moire graphene models. So the purple one is the one corresponding to twisted bilayer graphene aligned with HPN, the model that I have presented earlier. But other models correspond to other moire graphene problems, such as twisted double bilayer graphene, the system where you have one aligned bilayer, another aligned bilayer, and then you twist them compared to one another. Another color corresponds to tri-layer graphene aligned with HPN. So various problems where you have moire structures and where you have a Chern narrow band. And you see there's not really anything systematic we can say about how robust these systems are, but other than saying that mainly, first of all, we verify that flat band ferromagnetism is indeed present in the flat band limits, and then it is robust up to some limit. And so NS is the number of points in the Brunel zone. So this is basically an attempt at a thermodynamic extrapolation. So as you go to the left side of the plot, you go to larger sizes. And depending on the model, it's more or less converged, but it gives you an idea of the robustness of the state. Now, to go beyond the nature of the ground state, we can also look at excitations, and more specifically charged excitations, because they are the ones that will determine the transport gap. So in quantum Hall, in regular quantum Hall, the lowest energy charge excitation is a skyrmion anti-skyrmion excitation. So skyrmion is a spin texture, such as what's represented here. And because it has a charge C, you can form a charge excitation by forming a skyrmion. And numerically, the easiest way to calculate the energy of a skyrmion is through the spin stiffness, because the energy of a skyrmion is actually proportional to this spin stiffness. And the spin stiffness can be extracted from a spin wave analysis. So here I have the dispersion relation of a spin wave. So basically, it's just the exact energy of the system when you starting from the fully polarized state to just flip one spin. So basically, what I'm doing is just looking at um, a sub block of the Hamiltonian that has just all the spins, all the values aligned, and all the spins aligned except for one, which is reversed. And because this is almost fully polarized, this is a relatively small Hilbert space, so it's possible to go to quite large sizes and obtain this nice data collapse for various system sizes. This corresponds again to numbers of number of points in the Brownian zone, or if you prefer, number of electrons. Since it's spinning one, it's the same here. And then by extracting the slope of this relation of E versus Q square, I obtain the spin stiffness, which I have extracted here again for various models, various parameters, various moire systems. And here there's something systematic that emerges, which is that the spin stiffness is larger when the fluctuations of the Berry curvature are larger. So what we learned from this is that the skyrmion energy will be larger when the Berry curvature in the band fluctuates more. There are actually, since then, there have actually been some other papers which have shown some analytic relations between the spin stiffness or skyrmion energy and Berry curvature and quantum metric. So there was a paper by Zalatel, Bolting, and Chatterjee, and also a paper by Wu and Dasarba that explored these various relationships analytically. But since this skyrmion energy can increase due to band structure properties, basically, because that's what the Berry curvature is, it's a band structure property, we can wonder about other excitations, whether other excitations can become more favorable. Can they have a lower energy? And namely, another possibility in the system for a charge excitation is just to form a particle-hole pair that you fully separate. And so this calculation was done by a master student at MIT who worked with us and calculated both the energy of a skyrmion anti-skyrmion pair in green and the energy of this particle hole pair in red, and showed that there was indeed a crossover. So here the x-axis corresponds to the relaxation ratio. So this relaxation ratio is the ratio of the tunneling term between A and A sites between the two layers and A and B sites in the two layers. And what's very interesting about this parameter is that there's actually a limit in, if you take WAA to be 0, if you take this ratio to be 0, there's actually no Berry curvature fluctuation. So what you end up with is something that is almost a Landau level. But as you increase the relaxation ratio towards 1, the Berry curvature fluctuations increase monotonically. So increasing this ratio is a way of observing the effects of stronger Berry curvature fluctuations. And here, the realistic value, or what's estimated to be realistic in this system, is around 0.8. So at this value, according to Jenny's calculation, the particle hole excitation has a smaller energy than the skyrmion excitation, but it's actually very close to the crossover. And since we don't have like an extreme degree of precision of the band structure in this system, it's possible that either may be realized in the system. So I find that quite interesting because it's one of the it's a phenomenon that is quite similar to a quantum Hall phenomenon, but that is also very distinct. It's something that because you have these very curvature fluctuations, you can have new physics that doesn't appear in quantum Hall physics. Okay, so now if I have a little bit of time, I can tell you about the fractional case. I only
Yeah,
have
sure.
2 short slides.
Yeah, go ahead, go ahead.
Okay, so up to now, I have only talked about integer filling, but it's very natural to wonder what might happen if we had a fractional filling, because we have a Chern band, or so a Chern with whole conductance non-zero, and this band is almost flat. So we know that those are two conditions where fractional quantum Hall physics can in principle emerge. Or this is something that's been studied a lot in the context of fractional Chern insulators. And we know from this literature that those two things, the narrow band and the Chern number, are two necessary conditions to obtain functional Chern insulator, but they're not sufficient conditions necessarily. And one needs to study the model numerically as well, to be able to conclude about the stability of a fractional Chern insulator. So this is what we did in a different work. And to choose which fraction we wanted to look at, we used experiments as a motivation. Because in principle, you could say, okay, let's study fraction 1/3. It's the Laughlin fraction. It's the first one that was observed in the fractional quantum Hall effect. It's the most robust one. The only problem is, if you look at the fraction 1/3, there was actually no value polarization that was observed. Meaning, and as you remember, you need value polarization to obtain a Chern that is non-zero. So that's a little bit troubling. But on the other hand, value polarization was observed at numerical 3 and around numerical 3, and in a regime, in a window that includes 3 plus 1/3. So if you think about it in the whole picture, this corresponds to 4 minus 2/3. So really, what we should be looking at is the physics of 2/3. It's like having a Landau level filled with at 2/3 fillings with holes. And for this filling fraction, there are actually two candidates, two main candidates, which are both fractional quantum Hall states. They both have a Hall conductance of 2/3 times the quantum of conductance. One of them is spin polarized, it's a ferromagnet, and it's just the particle Hall conjugate of the 1/3 state that I was referring to earlier. And another one is a spin singlet. And actually, these two states in regular fractional quantum Hall, they actually compete depending on the value of the Zeeman energy. And if the Zeeman energy is small enough, the spin singlet is the one that wins. So we wanted to see, well, first of all, could we see any sign of fractional quantum Hall physics at 2/3? But also, could we see which spin order it would be in twisted bilayer graphene? So maybe I should be clear at this point that no fractional quantum Hall state has been seen yet in experiments. So the motivation here is more to see if there's a chance to see it, and if there's a strong motivation to go to lower temperatures in these experiments to try and see these states. So here are our results from hexagonalization. Again, very similar technique as what I showed in the integer case. So first of all, looking at the low energy spectrum, a good sign of a fractional quantum Hall physics is to have a degeneracy of the ground state with a gap, which we observed is a threefold degeneracy of the ground state and a gap to higher energy excitation. Second thing is you can do some flux insertion, which is a way of determining the Hall conductance. And we see that the three ground states flow into one another with a 6 pi periodicity, a sign which is compatible with the expected hole conductance for these two states. And finally, depending on the band structure parameters, we observed either a spin polarized state or a spin singlet. So both of the candidates that I mentioned earlier that are that exists in regular fractional quantum hole physics, we both saw them numerically. And actually, what we saw was that the obtaining one or the other, that competition is actually determined again by the Berry curvature fluctuations. And in fact, when the Berry curvature fluctuations are very small, you obtain the spin singlet. This is not a surprise because when Berry curvature fluctuations are very small, it means basically what you have is a Landau level. So you obtain the same physics. But as Berry curvature fluctuation increased, we saw that the ferromagnetic effect became energetically more favorable. And this is something that we don't have an explanation for at the moment. But it is quite exciting to see that there can be this interplay between Berry curvature and spin order. And this is again something that is quite different from regular Landau level physics. All right, so this brings me to the end, more or less. So let me acknowledge my collaborators. So a large part of this work was done while I was a postdoc at MIT and also a little bit after, in collaboration with Senthil and with 3 grad students. So Jiwan Dong and Yavi Zhang were both grad students at the time, and Yavi now has moved to Harvard as a postdoc. And Jenny did her master's thesis this year on this topic as well and provided some of these calculations. So with this, I will conclude by saying that with the drift, graphene can acquire many interesting and desirable properties, such as strong correlations. We've explored at integer filling the phenomenon of flat band ferromagnetism, and shown the strong role of Berry curvature, and finally showed that a fractional filling, a fractional quantum anomalous Hall effect was possible at, well, the gaps that we calculated showed that they correspond to temperatures that are in principle accessible to experiments, but are also temperatures that have not been explored yet in this context. So with this, I thank you for your attention.
Thank you. Thank you very much, Cecile, for this nice talk. So we had a few questions, but maybe there are other questions. So just raise your hand or unmute yourself and ask. Yeah, Ridish.
Yeah, so I think I missed a very simple point, which is, so when you say at integer filling, what exactly did you mean?
Yeah, so that means maybe let me go back to this picture. So filling, so if I take those, yeah, maybe I take just this.
Right.
So I have these 2 bands, and if the Fermi level sits in the middle where the Dirac point used to be, this is filling 0. This is charge neutrality. And if I completely fill the conduction band, this is +4. And if I'm below the valence band, this is -4. And so it's integer in the sense of taking into account the degree of freedom of spin and valley, which make each of these bands 4-fold degenerate. So for example, filling 1 is the largest filling I can have, where if I fully fill the band that has spin up and valley plus, then I will have a filling 1.
So then if I stick to the terminology of 4, then there are 1/4, 2/4, 3/4, and 4/4. Like I can have,
Yes.
right.
Exactly. Yeah.
So in this terminology, which case did you consider for this calculation?
So what I showed was one. We also did two, which is a bit different. And actually, in the model that we consider, 1 and 3 have a particle hole symmetry, which makes
Right.
them equivalent. But 2 is a little bit different. Typically, we see that it's a little bit less robust, but still um, there is flat band ferromagnetism as well. Except for 2, of course, um, you can't polarize everything at the same time. So there will be a large, within the model we have, which has a lot of symmetries, there will be a large degeneracy.
Right. So my question was basically related to that. I wanted to get a sense. So experimentally, I know that most of the ferromagnetism signatures have been observed in 1/4 and 3/4.
Yeah,
Well, depending on conduction and valence band also, seems to be an asymmetry. So do
yeah,
you have a sense why the physics is different at half filling and quarter filling, meaning 2/4 and 1/4 or 3/4?
yeah. Um, so maybe I can comment first on 1 versus 3,
Mm-hmm.
because I think it was observed at filling 3,
Right.
but not at filling 1. Okay, so my answer may be not very um, completely satisfying because I cannot tell you why it's 3 and not 1, but I can say why there's a difference between the two, which is just because of interactions you have just within mean field. You can see that the bandwidth will be renormalized a lot. So pinning 3 and pinning 1 actually have very different bandwidth. And I have not done those calculations myself to tell you which one has the larger bandwidth. But if I had to bet, I would say this might be the reason that once you look at the renormalized bandwidth, one has a larger renormalized bandwidth than the other.
I see. So it boils down to energetics. That's what you mean at the end of the day. That's your sense.
I mean, that's my guess, but that's because it's the simplest explanation I can think of.
Right.
Not because I actually have done the work of doing the calculation.
I see. And the other related question that I had was, so if I take a standard half-filled band and go to large U limit, typically it will give me an antiferromagnetic coupling, right? The standard TJ situation.
Yeah.
Here, that's not what happens, and presumably the fact that this is topologically non-trivial plays a role. So it is not just energetics; it also has to do with the fact that it's a Chern band.
Okay, so let me add a nuance to that. I agree that it's not just energetics, but it doesn't have to be a Chern band in the sense that the same thing can happen for trivial bands. What is necessary, though, is to have enough very curvature fluctuations within these bands, because this will increase the the overlap between wave functions, and that will have a role on the strength of the exchange term. So basically, if you take a trivial band,
Uh-huh.
um, you can always define fully localized Wannier wave functions.
Right,
And so you can derive a lattice model, basically, is what that means.
right, right.
And you'll have exchange terms in this lattice model that are ferromagnetic, and their strength, as long as it could do something very artificial and just if I'm not changing, I take a model and I just keep the wave functions the way they are, but I go to the flat band limit by just removing the dispersion. So I can go to the flat band limit without changing this term at all. But on the other hand, there will be a super exchange term which will be antiferromagnetic, and that term should go to 0 if the bandwidth is brought to 0.
So, but what I don't understand is if you are calling a band trivial, then what exactly do you mean by very curvature fluctuations?
Oh, yeah, sorry. What I mean by trivial band is just C equals to 0, Chern number equals to 0.
Okay, so there are still local pockets of very
Exactly.
curvature is just canceling.
Exactly, exactly.
Right. So in the truest sense, like if there is no Berry curvature, it will never give you ferromagnetism.
Yeah, absolutely.
Got it. Yeah. Thank you.
Yeah. If you if you really have the atomic limit, like if you really take the atoms
Right.
infinitely far away, then the corresponding orbitals never overlap, so there's no exchange, and then there's no ferromagnetic interaction. So yes, absolutely, I agree.
All right. Thank you.
Okay, we go to the next question. Sumiran, yes.
Hi. When you presented the results on the skyrmion energies, that was the background of the ferromagnet, right? I mean, there's say one skyrmion in the presence on top of the ferromagnetic background, something like.
Yes.
So, I mean, normally when we have a ferromagnet, we also think about spin waves, and they can also form some bound states, right? So, where are they in this discussion?
Sorry, I'm not sure I really understand. You're talking about the
So, if I have a ferromagnet, I will also have associated spin waves, right?
sure, yes, which are basically what is represented here.
Oh, so
So
this is a spin wave dispersion, the top left panel.
yeah.
Aha. So then where does this fermion come in here?
So it's just an easy way to extract the spin stiffness is from the spin wave itself.
Correct.
So that's why I'm calculating the spin wave, is to obtain the spin stiffness so that I can obtain the fermion energy. Here, of course, the spin wave excitation exists, but it doesn't provide me with a particle hole excitation that can carry a current. And here that's what I was restricting myself to, because I wanted to obtain the gap that is involved in transport experiment, right? Like we have an insulator, so the conductance will be given by an activated law with an energetic coefficient corresponding to this gap, to this particle hole gap. And so that's why the particle hole excitations I can consider are either a particle hole pair that is a well separated particle hole pair, and also a skyrmion anti-skyrmion pair.
So, but this fermion anti-skyrmion is not in the magnetic configuration then, or is it in the magnetic configuration? In the ferromagnetic configuration. Hello.
Maybe there is a connection issue.
Oh, okay.
Let's wait for a few minutes. Maybe she comes back.
Yeah.
Hi, Cecilia.
Hey, looks like I got disconnected.
Yeah, no worries. So, you want to share, you can share.
Okay. Yeah, so I don't know where I was cut off.
It was on
But
the
I should.
yeah. So maybe I just misunderstood what you refer to when you say charge C skyrmions, at the top.
Yeah.
What does it refer to?
It's that if you form a skyrmion in a band that has Chern number C, then it will have a charge C. So
Okay.
now
It's
that means
it's fermionic configuration in the Berry curvature. Is that what you have in mind?
oh no, it's in the spin,
It is
the
in the
actual
spin.
spin.
It is in the spin. I
Yes.
see. And okay, so I have the ferromagnetic configuration. I form a skyrmion, and you measure its energy with respect to the ground state energy, right?
Yes.
And so that is what E minus E naught by U is, right? On the top left panel, or no?
Not quite, because no, that's the spin wave energy.
Okay,
So
okay.
E naught is the ground state energy, and E is the spin wave energy.
I see. So then how do you make the connection that the increase in the spin stiffness with the Berry curvature also implies increase in the skyrmion energy?
Oh, okay. Yeah, that's the right hand side picture.
Uh-huh.
Um, so um, yes, so it's just that by taking, so here we did it just phenomenologically, numerically, we computed the spin stiffness
Mm-hmm.
for various models,
Mm-hmm.
which happen to have various very curvature fluctuations.
Right, right.
And we just saw where the point fell on the curve, and that gives you this. And then from this, I see that if I'm taking always the same model, um, so I'm taking one color, for example, when I increase the Berry curvature fluctuations, I also increase the spin stiffness.
The stiffness. And then,
Yeah,
am I right in saying that if the stiffness increases, I expect the increase in skyrmion energies? Is that
absolutely. Yeah.
okay? But sometimes even the spin waves can themselves form bound states, right? Is that
Well, that I don't know. Maybe
okay? Okay, so that you have not considered.
no.
Okay. And one final thing in your final slides, when you say n equals 8, 10, 12 in your exact diagonalization study.
Oh yeah, that's
Okay.
the number of electrons.
So, but physically that corresponds to some 8,000 lattice height, actual physical carbon sites or something like that.
Okay, so yes, so the reference is that you take a system where you project everything on the conduction band.
Mm-hmm.
So you're not counting all the electrons that would be in the remote band, right?
Sure, sure.
And then yeah, 8 electrons is then you have a feeling of um,
So you have 8. How effectively how many lattice sites? You still probably have 8 cross. I don't know, 8 lattice sites or something.
yeah. Let me just think for 1 second. Um, yeah, it should be 12 to have a 2/3 filling.
Yeah, yeah. I mean, whatever order n in this graph, it is that many lattice sites you have in your simulation, right?
Yes, but lattice as in super lattice,
Yes, yes, I understand.
right?
Yeah.
Yeah.
And then you have effective parameters, which are some hoppings in the superlattice and that kind of thing.
Yes, sure.
Okay, actually now I'm confused. So how many electrons are there in your simulation?
Uh, there are 8. There are really 8.
There are really 8. But
Yes.
in the physical system, there are definitely more than 8 electrons, right? Even if I had 8 superlattice sites.
Um, okay, let's forget about the fractional filling because this makes things confusing.
Sure,
But
sure.
if you are filling 1, you have 1 electron per moire unit cell.
But each moire superlattice is some 1,000 atoms, right? So there should be at least
Yeah.
1,000 pz electrons, right? So where are all those other electrons going? You see, is this question sensible?
No, Sumiran, I think he has projected everything on the band.
Yes.
So it is a projected simulation.
Okay. Okay, then at least I don't see it. But yeah, okay, that's fine.
Yes.
Thank you.
Maybe
Yes.
we
That's
can
correct.
discuss this offline
Yeah, yeah.
because we have two more questions. Sorry.
Yeah, yeah.
So
Okay.
there is a question. Was a question by Subhajit Sinha. You can ask the question if you want.
Yeah, thanks for the nice talk. So probably I had a very naive question. So in the initial part, you said about these two ways of engineering the anomalous Hall effect. So one is one other way you said is like the doping of the magnetic doping in TIs, and I was just wondering is there is any added merit to this approach of engineering the AHE state in this Chern band via polarizing Chern bands in twisted double bilayers, or would you say both have same merit? Yeah.
Yeah, well, if you look at gaps and temperatures, it's actually the I forget the exact temperatures, but the quantum anomalous Hall effect in twisted bilayer graphene can be observed at larger temperature, much larger temperature than the one with magnetic doping. So I think there's actually an inversion of the activation gap of transport and of the Curie temperature. So it takes, you know, the limiting factor in those doped impurity system is really the gap that you can obtain, the transport gap, because it's so small that you need to go to very low temperature to see insulating behavior, whereas it's much larger in this intrinsic system.
Okay, I see. You are saying that in future means this has merit in getting AHE to higher temperatures or something.
Yeah.
Yeah. Okay.
Yeah, I think.
Okay.
Yeah. The other thing is the fact that you have a flat band means, you know, in this twisted bilayer system, there's much more engineering and control that you can do.
Yeah, sure.
And also and control of the filling also of the because of the fact that it's gated. So I would say, you know, if you're ever going to see a fractional Chern insulator, I would put my money on this one rather than the impurity doped system.
Okay. Yeah, I was another question I had is from an experimental point of view, do you have any proposal as to how control Berry curvature fluctuations? Means one way I can think of like applying an electric field and tuning bands locally or something. Do you have any added suggestions?
No, it's a very good question. I mean, you know, anything that you change in the band structure will change also the Berry curvature. Then the question is how to actually control it. So the parameter that I've been using in these results is the relaxation ratio, but of course it's you know, you don't choose it. So no, I think it's a great question, but I don't know how to do this.
Okay, thanks a lot.
There is one small question. Let me read it in the chat box. So, with the artificial kinetic energy term, where is the information about flat band or magic angle is remaining in the Hamiltonian?
Where is the information about what?
About the flat band or magic angle is remaining in the Hamiltonian. With this, yeah.
Yeah, so I don't know if it's the sense of the question, but even at magic angle, the band is not completely flat. So first of all, you're never exactly at magic angle, you know, and then you have some band renormalization due to the interaction with remote bands. So yeah, it's just not exactly flat. I don't know if it was this. What was that?
I don't know. Maybe it was about whether is there any means where is the information about magic angle in the cosine term, something like that.
No. I think, you know, all the. I don't know if it's really the question, but you know, one thing what one might wonder is where is all the interesting properties of the band structure hidden. Right. And by interesting properties, like the wave functions themselves, actually it's hidden in the projection here. And where I can see this is in the form of some form factors that I wrote actually here, right? This form factor, like when you write down the projected density operators in terms of creation and annihilation operators, here there's an overlap between log wave functions. That's what I call a form factor, and that is where all the interesting physics is hidden. That, you know, these form factors are what are going to determine whether you have a large or small exchange constant, whether you have a Chern number or not, whether you have lots of very curvature fluctuations or not. This is where this is all hidden.
Yeah. Okay, I think that's it. Thank you very much, Cecile, for this nice and very interesting talk. I also thank everybody who participated in the chat and also in
thanks
this
for
room.
having me and for the interesting questions.
Right. Thank you very much. I thank for everybody. Yeah.
Yeah, I hope at some point I can visit in person.
Right. Absolutely. Hopefully soon.
Yeah, who knows?
Yes.
All right.
Okay.
Okay.
Thank you.